Done.
Got it. So welcome everybody, and thank you for joining us today for this Fleet and ANSTO run talk about the Centre for Accelerator Science, or CAS, from ANSTO. So before I introduce the speakers today, I'd like to first acknowledge the traditional custodians of the land on which we work and live. Many of you will be joining us from locations across the country, but for us at ANSTO, we'd like to pay our respects to the Dharawal people and recognise their continuing connection to the land, water and the community. I pay respect to elders past, present and emerging. So today we're going to hear from some brilliant scientists from the Centre of Accelerator Science. So that's Ceri, Zeljko and Armand, who'll introduce the capabilities for advanced materials modification and characterisation available to Australian scientists. And they're going to present some really nice examples from recent work on their accelerators. We're also very lucky today that we will be joined by a special guest, Professor Rob Alleman from the ANU Australian Facility for Advanced Ion Implantation Research, and he'll have some words to say to us at the end. So as per usual in a Zoom talk, please mute yourselves during the talk and any questions can be put in the chat or asked at the end of the talk. So with that, I'd like to pass over to Ceri, who will start us off. Thanks, Ceri.
Morning, everyone. Thank you for joining us for this webinar this morning. We're going to introduce to you some examples where we've been using ion beams to design materials of the future. So we've come from the ANSTO Centre for Accelerator Science, and Rob's joining us from the ANU Australian Facility for Advanced Ion Implantation Research. We are both facilities that are proud members of the National Collaboration for Research Infrastructure Strategy. It's an Australian government initiative that supports research infrastructure across Australia, including the Australian Centre for Neutron Scattering, CAS and ANU as part of the heavy ion accelerators. So in terms of accelerators in Australia, we are in a really great and privileged position to have these fantastic facilities available for research, innovation and science, asking all these interesting questions and challenges that we have for advanced manufacturing materials of the future. And they're all available to you, to everyone, at any time for any question that you have through our various user program and user access schemes. So today, as I said, we'll give you a little introduction to how ion beams can be used for advanced materials. What does that mean? What is ion implantation and what can it do for you and your materials challenges? And then towards the end, we'll have plenty of time to ask questions and start the discussion going about how we can match make our capabilities for the questions that you have. So at ANSTO, we are Australia's home of very large research infrastructure. ANSTO's been around for over 60 years across 3 sites in Australia, Lucas Heights, where we're based in New South Wales, as well as Victoria with the Australian synchrotron. Lucas Heights is the main campus where the nuclear reactor is, that's used for research and nuclear medicine purposes, and is also where the Centre for Accelerator Science is based. So the Australian Centre for Neutron Scattering is where you can have a whole suite of neutron capabilities for characterisation right down at the molecular and lattice structure level. And it uses the neutrons that come off from the nuclear research reactor. And there's a whole suite. That's where Ceri is based and her expertise. So anyone got any questions about neutron characterisation, I'm sure Ceri will be happy to answer those. The Centre for Accelerator Science is where we use ion beam accelerators for all different types of applications, where we support research and industry communities to explore the past, understand the present and design for the future. We're all obviously today talking about that latter part where we're designing materials for the future. But just to give you an example, this very morning, we had a press release put out about some of our latest research where we've been applying accelerator mass spectrometry for radiocarbon dating of precious Aboriginal artifacts. So if you'd like to know a bit more about that, it's on the ANSTO website on the top of the news page. So just hot off the press, a little bit about how we look at hundreds and thousands of years in the past, but we also apply these accelerator science capabilities for thinking of new and novel innovations for the future. So how do we support you and support the community? Well, we have a whole suite of capabilities that give you ultra sensitive analysis. So that covers radioisotope dating, trace element and actinide isotope analysis, all with world-leading sensitivity. Accelerators and ion beams can also deliver precision irradiation. So that gives you surface engineering capabilities as well as characterization down to the micron resolution. You can also ramp up the irradiation so that you can deliberately induce damage in materials and test how they behave under extreme radiation exposure conditions. And of course, that's the kind of bit that we'll be talking about this morning. And an important part of all of this is our end-to-end user provision. So when you come to the Centre for Accelerator Science, we will support you throughout your full research journey, right through from those first ideas and these kind of interactions where we're asking, can this happen? Can you apply the beams to do this? What I want to answer this research question, how can accelerators help us out to do that? So we'll hold your hand right through from that beginning through to designing a proposal and giving you advice on how to propose for time, right through to experiment planning and then data interpretation right at the end through to publication and impact. And of course, we are a working national research infrastructure. We welcome students, early career researchers, and anyone who wants to come and train and skill themselves up in the skills and techniques available within Accelerator Science and beamline capabilities. So how do you get access? It's very easy. Head to the website at the top, portal.ansto.gov.au, and that gives you access to all of our facilities. Twice a year, we open up a proposal round for free access to the capabilities. As I said, that's 2 proposals rounds every year, every 6 months. The current round that's open now is closing in February 2022 for access from July 2022 onwards. And that's a peer-reviewed competitive access process where the proposal is ranked on scientific merit and then is approved according to our capacity at the time. But typically around 80% of our users come through this scheme. So we've got plentiful capacity for this scheme. There's no charge, as I said, it's free, but there is an expectation to publish, this being publicly funded research. We want to make sure that those results and that information and knowledge is available to the global research community. And there's also, in some cases, support for travel and accommodation costs for you to come to site and do your experiments with us. Of course, there's another way as well. If you can also pay to access if you would like to take capabilities or take advantage of our commercial contract access, which includes the full scientific consultancy experience right through to planning and to interpretation. And that's particularly interested if you need and require proprietary access. So if you're looking at developing an idea that will be taken through for intellectual property protection and patenting, then that's normally where you will need to protect the results. It's also important if you really need to get timely and rapid access because it gives you a minimal waiting period. So there is about 10% to 15% of our users take this approach each year as well. And then there is a discretionary route, which essentially if you come straight through to the scientists or through to myself, and you could discuss your rapid access needs for very crucial high impact work, to rapid access needed to complete a publication or to support a student thesis just to get them across the line. And again, that's continuously open all rounds. You don't need to wait for those closing periods every 6 months, and there's no charge and support for travel as well. But that one, that one really would needs a kind of conversation with us to explain the justification on that sense. So once you've got access via any of those routes, then you're welcome to come and schedule your experiment and start your research journey with us. So I'll now hand over to Zeljko Pastuovic, who'll be able to introduce to you our capabilities in ion implantation, particularly for the topic of today, which is designing materials of the future.
Hello, nice to meet you, and I'm very pleased to give you information about our capabilities and also to present a couple of case studies. So here you see the schematical overview and detailed designs of a couple of our beamlines on a new series accelerator system. And the most important instrument for this particular talk, which is dedicated for case studies for material modification and how we can use a material modification to customize and fabricate customized materials, is low energy ion implanter. And low energy ion implanter is an instrument which produces beams of ions of low energies. In our case, we can produce beams of energies between 5 and 50 kilo electron volts. And ion implanter is part of the larger system. So you can see in the middle of the picture, it's a schematic presentation of our surface engineering end station, which combines the beam, low energy ion beam from the ion implanter with the high energy ion beam from the accelerator, which can be used for ion beam analysis. Next slide, please. So the low energy ion implanter of ANSTO is a fairly robust and simple system, which is designed for research purpose. So it is capable of running beams of many different type of ions. Here you can see in my periodic table type of the ions that we can run. So we can run a majority of metallic ions, and we can also run ions from gases. If we run gases, then we have a very high current beams between 10 to hundreds of microamperes. If we run metallic ions, they are produced by sputtering a metallic target. Also, what is important is that it is a standalone system, so it can be used by itself, and also it can be used as a dual beam end station as well. So the main purpose of our ion implanter is to produce changes or modification of structure materials, to produce defects, and we can produce isolated defects, which can be utilized for quantum sensing, or we can produce a large number of defects, which induces changes, significant changes to material, or even doping. So what happens when we irradiate the material with low energy ion beam? So we utilize ions. One great property of the ions, and that's that they have a very well defined range in the material. So what you can see on the left side is the distribution, ion distribution of 40 keV carbon ions being implanted in graphene oxygenated membrane, for example. And you can see that, you know, the range of these particular ions is, the peak distribution is around 100 nanometers. So, and by modifying the energy of the ion, we modify the penetration depth, or depth at which we modify the material. So this is a great property of ions, and the very precise depth at which ions are implanted and the rate at which they produce displacements is one of the best characteristics of ion beams used for material modification. On the right side, what you can see is, for example, when we irradiate 2D materials like graphene, that, you know, we can create point defects, single vacancies. Also, we can create double vacancies. Also, we can create additional carbon atom we can add to a layer, or we can produce complex defects like line defects or dislocations. Next slide, please. So one first example that I want to share with you is a project of dedicated to fabrication of synthetic diamond microsensor for neuroscience. And the significance of this research is that sensing on cellular level in biological systems is really important. And in order to satisfy all the requirements for biosensing, which is biocompatibility, chemical inertness, and also optical transparency is really a good property. That's the reason that in order to satisfy these properties, material properties or sensor properties, we've chosen to work with synthetic diamond. And the goal of this project was to produce a sensor which is capable of simultaneously electrical, optical, and chemical stimulation of neuron cells. Next slide, please. So how to fabricate that type of biosensor? So we developed methodology using a high energy scanning ion microbeam to implant carbon ions in diamond. And first of all, by doing this, we introduce defects. And if we introduce a high concentration of these defects, then the lattice of the diamond is completely destroyed. If the concentration is below the threshold for amorphization of a diamond, upon annealing, the crystal lattice can be recovered. In the regions where the concentration of defects is so high that the material cannot recover, upon annealing, material transitions into the graphite state, and by creating in very narrow region corresponding to the at the bottom of the picture, you can see the vacancy profile. And by implanting through the mask, we can actually create these conductive channels from the surface through the bulk of diamond to the central position where we can place the neuron cell, for example. And by applying electrical current, we can stimulate the cells. Also, by ion implantation, you also introduce a strain in diamond lattice, so you can change the refractive index. So you can use these channels also as a guide waves, so for optical stimulation of the cells. Next slide, please. So from here we went further, and as you know, the nitrogen-vacancy complex in diamond is a very interesting defect because it has a special property, and it behaves as a quantum center because we can distinguish different states. And by combining, by producing nitrogen vacancies, we can create a large concentration of this type of defects in material. So, and if we use, when we place, let's say, nitrogen vacancies in ambient where we have a magnetic field, then we have a splitting between different states. And we can use optically driven magnetic resonance and radio waves in order to excite the nitrogen vacancies into the higher state, and then we observe the transition into the lower state. And next slide, please. And so by observing these transitions between the states and the shift because of the presence of magnetic field, we can create a very, very sensitive magnetic sensor. And we discovered this method which enable us to distinguish or to have the sensitivity of magnetic field in the presence of nitrogen vacancies at the very surface of our diamond sensor of the order of 10 nanotesla. So that was a really great discovery. And not only that, but we also discovered that we can also observe a temperature shift in the region of millikelvin. So by developing this type of sensor, we have a possibility to excite and to stimulate cells, and we can observe all the changes in their environment. My next example is application to membrane technology. And as you know, the membranes, they are really important thin barriers that exhibit different properties like permeability or selectivity when they're subjected to different driving force. And driving force can be a pressure, concentration, temperature, potential difference. And the characteristics of this type of thin membranes is that when they are applied, they consume low energy. They have a very high separation efficiency. They're also environmentally friendly. So next slide, please. Karin, oh yeah. So we used again low energy ion beam in order to implant or irradiate very thin graphene oxygenated membranes. And by radiating them, we produced defects, simple defects like vacancies or complex defects. But the most important thing is that by creating these defects, we actually started creating pores through which ions and atoms can permeate. And by increasing the number of these pores, we can actually tune or modulate the permittivity of our membranes. Next slide, please. So here we did detailed studies, and we fine-tuned the fluence, and we implanted these membranes or irradiated with the fluence in the range 10 to the 15, 10 to the 17th. And depending on the fluence, you can see the changes in the structure and also the structural components and the changes in atomic bonds or the surface characteristics of these membranes. And also on the right side, you can see that by the first top image, or the left characteristic is the permittivity of the non-irradiated membrane, and all the other characteristics are showing increase of permittivity for different cations depending on the fluence or different treatment of these membranes. Next slide, please. So to finish, I would like to present the third study that we did, and this is a fabrication of thin magnetic layers in topological insulators that we did with University of Wollongong and with Center for Accelerator Science, Center for Excellence fleet. So the goal of this project or this study was to fabricate the nanostructures with magnetic properties in this topological insulator. So again, we implant the low energy chromium ions, and we implant it through the oxide layer through the tin oxide layer, titanium oxide layer into the topological insulators. And what we can see on the right side is that how the surface or subsurface implanted region changes upon annealing or in nitrogen atmosphere at 250 degrees. And also we can see from figure C shows that X-ray absorption spectrometry of the chromium L2 free edge in total electron yield and fluorescent yield mode reveal the chromium free plus valence state being formed in the implanted sample. So this all gives us a very nice capability how to fabricate the designed materials or materials with design properties, in this case with magnetic properties. So here I would like to hand over to Armand. He will show you a couple of examples of using this ion beam irradiation or implantation for energy materials.
Okay, thank you, Zeljko. Hopefully you can hear me. Okay, so this first slide is really just to highlight what we are all hopefully aware of, and that's the current global dependence on fossil fuels has major environmental and climate change consequences, as well as impacting a growing number of health conditions, as you can see on the right there, associated with breathing fossil fuel emissions that contribute to high morbidity and premature mortality rates globally each year. So these are key drivers for the ongoing focused research effort towards developing clean and sustainable energy technologies for the future, whether that be energy generation or energy storage. Next slide, please. Hydrogen is widely considered to be a major fuel for the future. As an energy carrier, it's abundant, it's storable, it's transportable, it's energy dense, and it's sustainable. However, one of the main hurdles is how to cleanly and cost effectively produce hydrogen gas, as in nature it's bound in compounds with other materials. One method is extracting hydrogen from water using electrolysis, known as water splitting. Next slide, please. So this is a basic schematic of water electrolysis, where an electric current is applied to electrodes submerged in water, and that drives the oxygen evolution reaction and hydrogen evolution reaction to split water into oxygen and hydrogen. Ideally, the electricity used to drive the process, as you can see in the bottom left, is sourced from clean renewable energy sources, and that's the hydrogen fuel can be used in a fuel cell, as you see in the top right, which essentially recombines the hydrogen and oxygen to produce electricity with the byproduct of water vapor. However, generating hydrogen this way is currently not cost competitive with fossil fuels. So one strategy is to try and improve the material performance of the electrodes. Next slide, please. So that leads me on to this first example, which is a recent collaboration with Dr. Chong-Yong Lee. He's an electrochemist from the Australian Institute of Innovative Materials at University of Wollongong. And this work was done under a ANSTO University of Wollongong seed funding program. So firstly, a little background. Developing high efficiency electrocatalysts is really vital for the production of hydrogen on a large scale by splitting water. Noble metal based electrocatalysts like platinum, ruthenium oxide, iridium oxide exhibit high electrocatalytic efficiency, but their scarcity and high cost really is a hindrance to large scale applications. So the aim of the work was really to develop low cost, highly active alternatives. Next slide, please. So as I said, this was a pilot study to explore a new processing strategy for developing iron-doped nickel electrocatalysts that combine metallic 3D printing capabilities at Wollongong Uni with controlled ion implantation, and to assess if these novel electrodes could actually improve the water splitting performance. Next slide, please. So this slide highlights really how this collaboration leveraged on the capabilities available at University of Wollongong and also the ion implantation at CAS. So we used additive manufacturing technique known as selective laser melting, and that uses a high-powered laser. You can see the image down the bottom to sequentially weld sectional areas of a designed component, allowing for the creation of complex and intricate geometries from a starting metal powder. So in this case, we produced and designed and produced a titanium conical array consisting of 407 cones. The cone heights were about 700 microns and the base diameter about 450 microns. And then we electrode deposited nickel onto this array, about 10 microns thick. And then ion implantation was used to implant iron into that nickel layer, overall giving material modification control on both the design array architecture as well as on the implantation parameters, as Zeljko touched on earlier, to be able to control the dose and also the depth. Next slide, please. So this slide shows the SEM and EDX results. From SEM on the top left image, you can see the cones from above, and you can see that the remnant spherical particles on the cone surface from the selective laser melting technique. What's important is the EDX image on the bottom right, which confirms that we had iron we could see iron after the iron implantation. On the right is the iron distribution curve, which shows that the depth of the iron implantation was about 5 nanometers from the surface. So within that 10 micron thick nickel film. Next slide, please. So this slide shows preliminary results of linear sweep voltammetry performed on these electrodes. So on both a non-patent electrode on the left and a patent electrode on the right for no implantation, for medium dose and a high dose implantation. And what you can hopefully see is that the implanted iron improves the catalytic current for both non-patent and patent electrodes and for both medium and high dose. So this suggests that the implanted iron has a positive effect or impact to increase the functional electrocatalytic performance in the water oxidation reaction. But while performance increases with increasing dose in the non-patent electrode, as you can see on the left, what's interesting is that for the patent electrode, there's almost a comparable performance observed for both implantation doses. In fact, the medium dose, surprisingly, showing slightly greater improvement than the high iron implantation dose. So as I mentioned, this is still a pilot study, so we're doing some further studies to try and better understand what's going on. But the early results show that this approach clearly has some potential to provide greater control than standard wet chemistry fabrication methods to systematically engineer electrocatalysts with optimal performance. Next slide, please. So this next example is research related to electrochemical energy storage. Next slide. So this work was a collaboration with Dr. Pramod Koshi from UNSW School of Material Science and Engineering. And this was accessed through what Ceri talked about, the ANSTO portal as well through one of the rounds. So again, I'll start with a little background. Current electrochemical energy storage technology is based on devices capable of exhibiting high energy density, such as batteries, or high power density, such as electrochemical capacitors. Pseudocapacitance is a Faradaic process. It involves surface or near surface redox reactions and offers another means of achieving high energy density. The significant difference between battery and pseudocapacitive materials is that the charging and discharging behavior of the pseudocapacitive materials occurs on the order of seconds and minutes, which can be particularly useful for energy storage applications where large amounts of energy need to be delivered or accepted quickly. The objective of the work was really a controlled synthesis strategy combining architectural design and defect engineering to investigate the effect on pseudocapacitive performance in cerium oxide nanoflakes. Next slide, please. So the image on the right illustrates the the fabrication process. Firstly, the architectural design component involves synthesis of the cerium oxide nanoflakes by a template-free electrodeposition technique at UNSW. Secondly, we modified the defect equilibria, intrinsic defects, by imposing annealing under oxidizing or reducing atmospheric conditions. That was done at UNSW. And then finally, we ion implanted the samples with molybdenum to incorporate extrinsic donor defects into the nanoflakes. And the figures at the bottom show AFM, the thickness. The ones on the left are from AFM, showing about 36 nanometers in thickness, and the SEM also a range of about 12 nanometers to 30 nanometers thick of those nanoflakes. Next slide, please. So this slide shows the results of chronoamperometric measurements done on the samples. Previous work by UNSW on cerium-based oxide pseudocapacitors showed that they suffered from an unbalanced charging-discharging rate, in that the charging took much longer than discharging, which can reduce both the energy and power densities. But in this work, the curves determined that the respective charge-discharge time ratios were 3.54 for the air annealed, 1.56 for the nitrogen annealed, and 1.33 for the molybdenum implanted nitrogen annealed sample. So it indicated considerable improvement in balancing the two processes, that charge-discharge, especially for the implanted sample, likely as a result of the introduction of both high oxygen vacancy concentration as well as the molybdenum donor defects. Next slide, please. Okay, so the figure at the top left is cyclic voltammetry, which showed significant improvement in gravimetric charge storage. The calculated specific capacitances were 328, 583, and 764 farads per gram for the air, the nitrogen annealed, and the molybdenum implanted sample respectively, representing about 130% increase in specific capacitance for the sample with the molybdenum ion implantation over the nitrogen annealed sample alone. The bottom left plot further highlights the enhancement in specific capacitance for the molybdenum implanted sample, and also with decreasing scan rate, which indicated the necessity to allow the electrolyte ions sufficient time to access the active sites. And lastly, the figure on the right, we assessed the capacitance retention using cyclic voltammetry for 2000 cycles. And what we could find was that the ion implanted sample had the highest stability at 95%. Overall, the molybdenum implanted nitrogen annealed sample exhibited the best performance in terms of gravimetric capacitance, discharge period, and capacitance retention. So hopefully these couple of brief samples show how ion beams can be used as an additional tool to modify the functional surface properties of advanced materials. Thank you. Hand back to Ceri or Zeljko.
Everyone, thank you very much for those examples. Before we hand over to Rob Ellerman at ANU, we just wanted to give you an idea of what's coming in the future. So Zeljko would like to just say a few words about some of the advancements that we're going to be taking on the low energy implanter to take it to ultra low energies.
Yes, please excuse us. We had a little bit technical difficulty, so we don't have the last slide included in this presentation. But we just want to touch briefly on the future prospects of CAS and how we can, let's say, deliver new or improved capabilities for this type of studies. So, as you know, there is a shift in terms of also low energy electronic materials, but also new novel advanced technologies to 2D materials. And the irradiations that we demonstrated in this case studies, they're based on KV ions that have ranges in materials between, let's say, 10 nanometers up to 100 nanometers. But we have a plan, and we actually would like to partner with interested institutes and groups to develop a new capability, and this is ultra low energy ion implantation. And it would enable deceleration of these kV energy ions down to maybe 100 EVs or even lower. There are a couple of concepts how this can be achieved, but mainly by applying the electric field which will stop the positive ions or just leave them with very, very small energy. So this is the plan for the next year or a couple of years to develop this deceleration stage and enable implantation of low energy ions, which would enable us to modify 2D materials. And also, unfortunately, I don't have a slide here, but the main purpose why low energies are required, because by lowering the energy, we actually can modify only few first atomic layers in 2D materials, or just one layer, depending on which energy we can achieve. Yeah. So that's for the future, and I think that it is a very exciting project, and we would like you to join us.
Brilliant, thank you for that, Zeljko. Over to you, Rob.
Thanks very much, Ceri. Look, again, I feel a bit like a gatecrasher at this meeting. It seems to be mainly an ANSTO fleet meeting, but I'd like to thank Ceri very much for the opportunity to present our capability. Effectively, this is university-based accelerator capability. It's the NCRIS Heavy Ion Accelerators capability. It has 3 nodes, one at University of Melbourne and 2 at the ANU. And I'd just like to tell you a little bit about our capabilities. We have a long tradition of ion implantation research, and I just want to illustrate those capabilities. So the 3 nodes are illustrated here. On the left-hand side, the Heavy Ion Accelerator facility, as it's called, is based in the Nuclear Physics Department of the Research School of Physics at ANU. It's based on a 14 MV accelerator, and most of the research activities there are in the nuclear physics regime. So nuclear physics experiments, accelerator mass spectrometry with a complementary activity to that at ANSTO. They're gearing up to do radiation hardness testing of electronics. And they also do some materials modification using the capabilities of the high energy accelerator. This is a regime called swift heavy ion irradiation. And it's used for things like producing nanoscale pores in polymer membranes and the likes. That activity is led, the director of that activity is Nanda Dasgupta, shown in the photo there. On the right-hand side of this slide is the Experimental Condensed Matter Physics Laboratory based at Melbourne University. The director there is Jeff McCallum. That activity is based on a 5 MV accelerator, single-ended accelerator, and has a real niche market in terms of high-resolution proton microprobe analysis. So ion beam analysis is certainly the forte of that group. But they also have a very large activity in quantum computing technology and have developed a dedicated ion implanter for mainly for phosphorus implant into silicon for the quantum computing activity. In the middle is the facility I want to concentrate on today. It's called the Australian Facility for Advanced Ion Implantation Research. I'm the director of that activity. It started, actually the activity itself started almost 40 years ago, but it's been at ANU for 30 years. And it was basically an in-house capability for our own research, but with the help of NCRIS, we now have made those facilities available to the wider community. In fact, in all cases, in all of these nodes, the facilities were pre-existing. So NCRIS has basically provided some enhancement, but also provided OPEX, operational costs, to allow us to expand the interaction. The focus of our group really is on ion-solid interactions, ion implantation, ion modification of materials more generally, and a fairly rudimentary ion beam analysis capability. So we do Rutherford backscattering and channeling analysis, and also hydrogen profiling by a technique called elastic recoil detection. So they're the three nodes, and I'm going to tell you a little bit about the capabilities of the middle one. So this is the AFAIR, the Australian Facility for Advanced Ion Implantation Research. It's based on 3 accelerators. We have a dedicated low energy ion implanter, which runs ion energies between 5 and 175 keV. Fairly broad range of impurities. It's a negative ion source, a sputter source. So it is limited in the, more limited than the high energy implanter. But we can heat and cool samples during implantation, and again, reasonable ion currents, typically in the microamp to tens of microamp range. We have a high energy ion implanter, which takes the energy range from 200 keV up to around 10 MeV, depending on charge state of the ion. This is a tandem accelerator, and I won't go into the details of how the tandem accelerator works, but basically it allows us to get to relatively high energies based on the charge state of the ion. The higher the charge state of the ion, the higher the accelerated velocity for a given potential. So energy range of 200 keV to 10 MeV. Again, similar temperature capability from liquid nitrogen temperatures up to around 450 centigrade. We do have a second beamline on this facility for 6-inch wafer implants, so 150 millimeter capability. That requires some special care to avoid ion neutralization effects in the beamline, and we have that capability with an electrostatic deflector towards the end of the end station to allow us to implant large area wafers without contamination from those neutralized ions. So fairly flexible capability in both cases here. The standard beamlines on both the low energy and high energy implanter are interchangeable. So samples can be moved from one to the other if a range of different energies are required. And the third accelerator here is used for ion beam analysis. As I mentioned, it's used for Rutherford backscattering spectrometry and ion channeling analysis, and elastic recoil detection for hydrogen and deuterium profiling. Our user base actually is fairly broad. Again, we have a lot of requests for just straight service work. We collaborate extensively with other groups, and in many that we're involved intimately in the experimental planning. And we also have our own in-house research activities. So the facilities I described were all developed to service our own in-house research. They were not designed originally for external service work, but they are now available for that purpose. You can see the list of collaborators here. I'd like to highlight a couple, and I'd like to make one point, I guess, and that is that a large amount of the work in the last several years has actually focused on quantum technologies. So we support most of Australia's quantum technology groups, including those at UNSW, University of Sydney, University of Melbourne, and also some new engagements with Microsoft, who have an activity based at the University of Sydney on quantum computing, and Quantum Brilliance, which is indicated under the government industry section here. Quantum Brilliance is an ANU startup based on quantum sensing and quantum computing using the NV Centre in Diamond. And actually their production at the moment is based on the use of our facilities. They use the low energy implanter for the quantum sensing activities where you need the active center, the NV center, to be close to the surface of the diamond. And they use the high energy implanter to bury the NV centers deep in the diamond for quantum computing. It turns out that the coherence between quantum centers is perturbed by the surface, and you need to be well away from the surface to maintain coherence. So that's an example where the full capabilities of our facility are exploited commercially. We do have interactions with centres of excellence, and we've even done some work for Fleet, I think with Julie Carell. We've done some ion beam analysis for her, but we'd certainly welcome any opportunity to expand that engagement. Okay, I'll go to the next slide, Ceri, in the view of the time. The research activities that we're involved in are fairly broad. A lot of the original work was in microelectronics and still involves microelectronics. So we have linkage grants with industry, again, in the microelectronics area. A lot of work on photonics, again, NV centers, things like hyperdoping of silicon for infrared absorption. A lot of work on photovoltaics, mainly at ANU and UNSW, studying processes like gettering, some ion beam analysis in terms of hydrogen profiling in hydrogenated amorphous silicon, work on doping in general. A lot of work on functional materials, so studying ion-solid interactions and how it modifies materials, things like synthesis of oxides. We've done work on 2D materials, again, defects in graphene, modifying the mechanical and thermal conductivity of graphene by ion irradiation, synthesis of graphene using implantation into metals, and so on and so forth. Quantum technologies is the big one. Again, it involves optical centers based on NV centers and other dopant defect centers in diamond, erbium in various materials, including erbium in silicon. And that involves actually, as I said, most of Australia's groups there working in that field, including corporate engagement with Quantum Brilliance and Microsoft. Again, very different approaches. The Microsoft approach is completely different to that used by Quantum Brilliance and the others, but again, exploits the capabilities of ion implantation. And we do basically some, as I mentioned before, fairly modest ion beam analysis compared to the capabilities at Melbourne University and at ANSTO, but they are complementary facilities that allow basic thin film analysis and ion channeling. So for the final slide, final slide. So look, the main strengths of our group are that we do have fairly flexible ion implantation facilities. We can vary the temperature, cater for different sample sizes and dimensions, and we've implanted everything from the facets on a 3mm silicon 28 crystal to bits of diamond to everything. We can usually cater for that fairly well. We have a strong track record of research in this field. Again, as I mentioned, I've been working in the field for over 40 years, started as a master's student way back when, and for the last 30 years at ANU, where we've built up the facilities for ion implantation. We are well connected nationally and internationally, so we have access to 2 and 3D simulation capabilities, and we have access to complementary facilities overseas. We're the only non-European affiliate member of the Radiate Consortium in Europe, and we share facilities and exchange capabilities there as needed. We've got strong national and international links. We have strong academic and industry engagement. And we do, as ANSTO does, have access to a variety of other fabrication and characterisation facilities, both at ANU and through ANFF and Microscopy Australia. So we, again, would welcome any form of engagement. And as for ANSTO, the access is fairly straightforward. We have various portals. You can come in through the ANFF node, or you can come in directly through the AFAIR website. Again, the engagement can be everything from service work through to collaborative work, and we would certainly welcome the opportunity to engage with you. So thank you very much, Ceri, for the opportunity to present that.
Brilliant. Thank you so much for everyone for those contributions. I hope that's given you a bit of a flavour of the things you can do with ion beams, particularly around this challenge of modifying and designing, fabricating quite advanced structures down to the kind of nanometer scale.
Yeah, so
Over to you,
I'll
Kerry.
take over there if you like. I know we are getting pretty close to the hour, but willing to hang on the line for a little while. If people have got some questions, please, by all means, raise your hand. You can put them in the chat. Happy to take questions. While you're thinking, I'm going to start with the first question. It's about homogeneity and control. Zeljko, you were talking about making single ion implantations and even lines of ion. What's the resolution like? How do you control the location of these implantations?
So the particular example that I showed is related to high energy ion microbeam. So in that particular case, we used 5 MeV carbon ion microbeam, which is focused down to 1 micrometer size on the surface of the sample. So how we control it, we use an instrument which is called nuclear microprobe, which is essentially ion microscope of MeV ions. And the system works that you have a system of lenses, electromagnetic lenses, that you use to focus the beam. And the good thing about the ANSTO microprobe is that we can focus relatively high energy and high Z elements. So usually the microprobes operate only hydrogen and helium ions or alpha particles, but we can focus also oxygen and carbon ions, and also heavy ions like silicon and stuff like that, which is really beneficial for this type of work where you want to use it for ion lithography.
Right, and is that strongly energy dependent? Because you were talking originally about low energy, and now you're sort of highlighting that it's...
Yeah, so in order to focus the high energy ions, you need very high, very strong magnetic field. So that's the difference. And also in terms of the low energy ion beam, because we operate a positive ion beam, so we have very high current. So we have also a high space charge as well when you focus the beam. So in terms of focusing the beam, we can focus down to maybe sub-millimeter size on our ion implanter, but we use the scanning to irradiate or to implant homogeneously over large areas. Right. And but people, for example, working in a Center for Excellence in Quantum Computing, they use implantation through the IFM tip. So that's how they position the single ion, and they use a particular technique which is called ion beam induced charge or a current to detect the ionization, which is corresponding to 14 kV phosphorus ion. Yeah. But that's done in Melbourne. Yeah.
Right. Okay. Thanks. So we have a question in the chat from Dave Cordy. This one's for you, Rob. What are the detection limits and spatial resolution for your setup for hydrogen profiling? What approximately?
Yeah, look, thank you for the question. Look, again, the elastic recoil detection technique is one of the few techniques that allows you to measure hydrogen, but it does come with limitations. And so it is based on having a relatively flat sample surface. It typically requires a sample of several millimeters to 1 centimeter in size. And it has the capability of detecting around 0.1 of a monolayer, 10 to the 14, 10 to the 15 atoms of hydrogen per square centimeter on the sample. Depth resolution is probably of the order of 10 nanometers or larger. So, and again, the other limitation of the technique is that there is always water vapor on the surface of a sample. So if you're looking at hydrogen at or right near the surface, that can be a major limitation. Again, we have done lots of experiments where we've substituted hydrogen for deuterium. That allows you to actually separate those effects and actually provides a bit more insight.
Great, thanks for that. Yeah.
In terms of bulk concentrations, about 0.1 atomic percent.
Right, okay. Do we have some other questions? I just wanted a clarification from Ceri, if I could. You mentioned at the beginning that the portal closes in February. Do we have an actual date on that? Is it the beginning, the end, the middle? When the portal for applications
yes.
to use the facility?
Where it is at the top of my head. I should be able to see that. 15th of February for ACNS, so all the neutron scattering. 28th of February for CAS. So it's actually slightly different depending on whether you want to do neutron scattering or you want to use the accelerator capabilities. So for accelerators, last day of February, 28th, otherwise the 15th.
Brilliant, excellent.
But those dates are on the front page on the portal website, the one that I linked to you.
Excellent. So if people, I mean, obviously we're quickly running out of time. So if people would like to learn some more information or perhaps to approach you with their specific scientific challenges that they would like to answer, they can contact you through the CAS website or the
yes, you
emails?
can. I'm also going to drop my email here right now as well, so you've got it, so you can copy it across.
Great idea. So are there any further questions? Has anybody perhaps from Fleet got a scientific challenge they're already considering that they'd like to bring up and share with us? Oh, excellent. So Ceri has put her email and Rob Elliman has also put his email. Rob, do you have any closing dates for your access to your facilities, or it's just?
No, it's basically, we can normally turn around within a couple of weeks. So basically people contact us, we schedule it and basically proceed. There is no application process.
Excellent. And just as a curiosity, how long do people generally get on your instruments? You know, do you get a day to do your measurement? Do you get a week, or it really depends on the type of science you're trying to achieve?
It depends on the science. You get what you need. Typically, we can do most jobs in one day. But it also varies. We do some work just as a service, but we also offer a training capability. So for example, the Quantum Brilliance technical team have been trained to use the facility. So they come in and they book time and they actually use the facility for their device fabrication.
Excellent. And how about you, Ceri? What's the typical time at CAS or Zeljko and Armand?
So again, that's negotiable on the needs of the experiment and the science. So we can do days and up to weeks. And we're now looking at opening up the idea of a kind of a programmatic access. It's a similar scheme that the ACNS runs, where you're able to actually apply for quite longer programs of access, coming back, every few months or a couple of times a year, if your research program really needs that regular access in order to keep asking the questions, keep trialing and testing ideas. So yeah, it's very flexible to meet the needs of your challenge.
Yeah, wonderful, excellent. So before we finish up, because I know
maybe
you're going, Zeljko.
Maybe just a comment. I mean, people who visited our facility or ANU facility, they know. Majority of time actually goes into preparation of the experiment because we operate ions. So every time we change the ion species or ion energy, we have to change the settings. This is not like, continuously running electron beam or continuously neutron radiation. So that's the complexity in terms of running these projects. And majority of these projects, let's say, where we introduce single defects to create certain concentration, which is below the amorphization thresholds and stuff like that, that can be performed within minutes, maybe up to hour, something like that for the highest fluencies. So it does not take very, very long time, you know, but it's the preparation. Right. And also making sure that you will not mess up the sample, because we all know how much single crystal electronic grade diamond cost. You know, you do like 10 test runs on test samples, and then you do the diamond.
Right. Excellent. So it's all in the preparation. That's what you're saying. That's wonderful. Excellent. Well, if I don't see any further questions, nobody's hands up at the moment, then this might make a nice spot to finish up. So thank you very much to all our speakers. Much appreciate the information. I've certainly learned a lot and have a lot of questions and things that I'll probably follow up on. So yeah, thanks very much. And yeah, have a great day.
Yep.
Thank you, everyone.
Thank you.
Thank you.